Okay, in today's class, we are going to learn a little bit about interconnects. Okay, so what is interconnect? Because most of the chips are many, there'll be millions of transistors, but they are interconnected with with wires. Okay, and those wires are known as interconnect. And what are these wires? They are small metal deposits on the chip, okay, which interconnects the drain, source and gates of the various transistors. Okay, so those metal deposits are called wires, and other terminology for that is known as interconnect. Okay, so when we make the stick diagram, generally we indicate the wires, and from that you can estimate what would be the total area of the chip, right? What happens is, in an actual chip, there will be many layers of wires, because initially they were only very few layers of when the CMOS technology started. There was only one or two layer of metals, but then slowly as the number of transistors increased, the routing started taking lot of space. So now if you see here, there was a condition where 70% of the chip area was being consumed by routing. Okay, so you had to keep these devices far off so that wires can be connected between these devices without crisscrossing each other, right? If you do the same metal, then to make these things compact, we started having many layers of wires, and since they are insulated from different layers of wires are insulated in between with silicon dioxide, they can crisscross each other, okay, without making a short circuit. So many layers of wires started coming in. Okay, so wires are as important as transistors, because in a VLSI chip, the speed, power, noise and area, they all get affected because of the wires also. Okay, so not only the device sizing, the sizing of the wires and the way we do the routing is also equally important. Okay, so in the back end, most of the guys who make schematic, they wouldn't be doing the layout and things like that, because that is again a very specialized job as of now. Okay, so there are people who continuously keep working on the layout aspects, and they are they know the techniques which are needs to be employed to reduce the parasitics which comes along with these wires. Okay, let me just increase the size of the mouse. Okay, so that, and then one thing which generally the alternating layers of the metal are run orthogonally. Okay, the orthogonally means at 90 degree, so that there is a least amount of capacitive couplings, because if you have two metal layers running one below the other, exactly one below the other, so the capacitive coupling will be greater. So generally what we try to do is, between two adjacent metal layers, we try to run them orthogonally or 90 degree, so that to minimize the capacitance between those two layers. Okay, so this is how a wire looks like. So there are certain definitions. This is the thickness of the wire. Okay, this is known as T. Okay, the small h is nothing but the insulator thickness, okay, between this and the next metal layer. Okay, so that is, this small h indicates the spacing between two layers. Okay, so it is filled up with insulator, generally SiO2. W is the width, and L out here will be the length of the wire. And the distance between the wires, okay, minimum distance is generally specified. Otherwise, S is known as the distance between two adjacent wires. Okay. So pitch is generally referred to as W plus S. Okay, that is the minimum width plus the minimum space is generally known as the pitch out here. Okay, and then we also have another term which is known as the aspect ratio, which is nothing but the width divided by the thickness. Okay, now in modern, initially you had an aspect ratio less than 1. Now we are having aspect ratio close to 2. Okay, we are able to reduce the width. Okay, that is because of the better lithography what we have, and with the technology moving towards a sub-micron level and coming towards a nano scale, we are able to have very thin wires. Okay, so thin wires generally we are able to packing density increases, right? And better routing can be done within a given limited space. Okay, provided we are able to draw lines. So why this minimum width is specified by each technology is, here it looks in a perfect, okay, a straight line out here, but when we actually deposit these metals, okay, so it won't be a straight line, right? So it will there will be some imperfections out here, right, on both the sides. Okay, and catering for those imperfections also, there should be a minimum gap. Okay, so otherwise there will be a break in the conductivity, right? Okay, so even with the worst case imperfections from both the edges, there has to be a good connectivity along the wire. So that is why we define a minimum width always for an conductor. Now if you see here, in 600 nanometer technology, it just had 3 metal layers. Okay, so most of the modern processors use 6 to 10 metal layers. Okay, whereas 180 nanometer processors, it uses 6 layers. Okay, so the first layer M1, which is the closest to the transistors. Okay, first it will be the transistors, and then you have an silicon dioxide, then you have a layer of poly. Okay, so the poly forms the gate in many places, and these days instead of a poly for what this is for 180 nanometer, you generally have poly, but for 45 nanometer and other technologies, the gate is made up of, because we know as the voltage, we have scaled down the voltage to reduce the threshold voltage. So we have changed the gate from poly to metals like molybdenum, tungsten. So they are the gate metals which are being used these days. So initially it was a poly, but again here also you have the first layer, generally you have the poly, and then on top of that you will have again an insulator, and then the metal 2 to metal metal 2, metal 3, metal 4. Each of these metal layers will have an insulator in between. Okay, so M1 is generally used for very thin interconnects. Okay, then M2 and M4 for thicker, and M5 and M6 for VDD, ground, and clock. Okay, so obviously if you are expecting large currents, will expect large currents to flow in the VDD rail, ground rail, and the clock. Clock will, because clock also is going to drive lot of circuits, so you can expect that there will be the currents in the wires which are carrying the clock will be higher. So that is why you use thick wires, and which is generally M5 and M6. Okay, and now if you see in this table, this is just for 180 nanometer. For layer 1, the thickness is just 800, width is around 250, and the thickness is 480 to 800. As you keep coming up to layer 6, the width is minimum width is 860, and the thickness is also 1720. That is just to cater for higher currents. Okay, so that is how these are the various metal layers which are there. For this is for just for 180 nanometer, where there are only 6 metal layers. Okay, now modern day technology, we do use aluminum is the one which was being used generally till 180 nanometer technology. It had a bulk resistivity of 2.8 okay, micrometer per centimeter into centimeter. Okay, this is an aluminum. This is the row. Okay, so it had just 2.8. Okay, but the thing is, it is cheap. Okay, compared to all other metals. So that is why it was being used. Okay, copper, it is got better electrical properties, but then it is definitely much. The cost is much higher than the aluminum, and also you need to take care that the copper atoms have a tendency to diffuse into silicon. Okay, gold is another very good option. It has got a much lower resistivity, but then the issue is it doesn't have this diffusion issue also, but then it is pretty costly. Okay, so this is the various metals which are being used out here. So tungsten and molybdenum, they are used generally only for the gate metal, okay, not for wires actually. So it is listed out here because we have started using this in the CMOS technology, so that is why it's listed out here. Titanium is also used for gate. We are using aluminum. I'll just show you one more slide. This is for 45 nanometer. Okay, so most of them are aluminum. Okay, I think that top layers are, if I remember correctly, the top layers are copper. Some of them are. Okay, so you have the 6 metal layers. And then you have the additional layers coming in for 45 nanometer technology, 65 nanometer technology. Even for 45 nanometer, there are these top additional metal layers are there. So the when you are doing a back-end design, okay, so several vias will be provided by the fab lab design itself, okay, which interconnects these various metal layers. Okay, generally. Like from one metal to other metal, adjacent 2 metal vias are provided, but I guess I just saw this document in which they are the fab lab is providing vias which connects like metal 5 to metal 8 via. Okay, so these kind of vias are also there. Otherwise, what we generally do is we have metal 4 to metal 5 via. Then on top of that we place metal 5 to metal 6 via, metal 6 to metal 7 via, like that. You stack vias one over the other to interconnect metals which are not adjacent. Okay, that was what we used to do, but I found this literature where they said some fab labs are giving vias which can connect directly metal 5, metal 8, and those kind of vias are also readily available in the technology library, it says. Okay, so I have not come across that personally, but it's there in the literature that these kind of vias are also available. Okay, now if let's get into some properties of these wires. Okay, rho is the resistivity. Okay, normal for any metal, what we know, this we know from our school days. So the resistance is given by rho L T by W. Okay, right. So if the length increases, the resistance increases, right? Whereas if the thickness and the width increases, the resistance decreases, right? Because if you see here, the thickness and the width is actually the cross sectional area. So if you have a bigger cross sectional area, so there will be it will be that much more easy for the electrons to flow, right? Whereas if the length increases, it is going to increase that much more friction, you can call it that way. So that is why you have the length in the numerator and the thickness and the width in the denominator out here. And rho is this is going to be common for any metal, okay, aluminium, whatever it is, this formula. Okay, L, T and W, this is the length irrespective of what metal you are using, T and W. Rho defines the properties of the metal. Okay, so the value of the rho will be different for different metals. Okay, that is what we saw here, right? So the rho rho will be different for various metals. A good conductor will have a rho value very less, and a bad conductor will have a high value of rho. Okay. Now specifically for VLSI chips, okay, we see that this T is not available to the designer, right? So this is already pre-decided by the technology, that what is the thickness of the wire which is going to be there, right? So the designer, the backend designer who is going to make the layout, now he only draws wires interconnecting. He has the flexibility to change this L and W. So this T is not a design parameter available to the people who design the layouts. Okay, that is a fixed parameter by the fab lab. So why to keep this out here in this equation? So we have defined a new way of defining the resistance, which is known as the sheet resistance. Okay, that is nothing but rho divided by T. Okay. So rho, that this T is also taken care of. So rho divided by T. So rho comes from the metal which is being used. Again, that is decided by the so for the fab lab can tell, okay, a rho for different layers of metal. For layer 1, a rho will be this much. Okay, this will the sheet resistance will be this much. For layer 2, it will be this much, and layer 3. So that gets defined by because of the various metals that is being used and the thickness of the wires which they are going to use while making these, while fabricating these wires. Okay, so now as a designer, I have this, so I have to I can play around with these two, L and W. Okay, and I have to minimize the resistance. Okay, how to do that? So I have to take care of this L divided by W. Now this would be in ohms. Okay, ohms per square. Okay, per square means so this square is dimensionless. Okay, so now this square is not L into W. So that's the mistake we tend to make. Understand, this is not when it square, we know, okay, length and width has to be catered for, and then we think square means L into W. That's not the case. A square is a dimensionless unit, and then dimensionless unit, sorry, and then it is defined by L divided by W. Okay, so that you need to take care. Okay, so you have to, if you have to count the number of squares, so R square will be given, okay, by the fab lab. If I have to compute R, so R square into number of squares. And what is the number of squares? L divided by W. Okay, so you have to be careful with that. It is not L into W out here. When we compute the number of squares, it will be L divided by W. So that aspect we need to take care. Okay, so this is about wire resistance. Now this is again for typical 180 nanometer. The sheet resistance for various metals it's given out here. Now if you see here for metal 6, the sheet resistance is the least. Okay, now why I highlighted these two is when we make the layout, okay, sometimes we find it easy for interconnecting the gates with polysilicon itself. Okay, even if they are very far off, you can do that, but you have to keep in mind whenever you are making interconnections of, say, two transistors which are close to each other, you need to, if you have to interconnect them with polysilicon itself, with the gate material itself, like I think we did it in the VLSI classes about layout. I discussed in detail in one class, where the gates can be interconnected with the gate poly itself. You can just extend when one is kept one over the other. So when the NMOS and PMOS, they are placed one over the other, in CMOS and static CMOS circuits, they can be interconnected with a poly. Okay, and few places where there this NMOS, two NMOS are placed adjacent to each other, and you can make a small polysilicon interconnects. Okay, but never try to make a big wire out of polysilicon, because it has got if you see here, it is almost 2 orders higher. Okay, the like it is 0.02, so it is like 100 times, close to 100 times higher sheet resistivity. Okay, so you got to be careful with that. So don't keep. So better option would be to place a wire and then use a metal to interconnect. If two transistors are placed far off, and you need to connect, even if you have to connect the gates of those two NMOS, both the gates are of poly. You want to connect it, so still you can put you can draw a metal one interconnect and use a wire, rather than stretching the poly for making a long wire out of polysilicon. Okay, so you need to be careful with that. Not that it cannot be done, so it depends on circuit to circuit, right? And also when I have to join two metals, okay, this is a via. Okay, so I have to ensure that to keep the resistance, okay, contact resistance as minimum as possible. So I keep these overlap area and place a large number of wires. Now here, if I see 1, 2, 3, 4, 5, 6, 7, 8 wires have been kept. Okay, what is wire? A wire is like from this metal to this metal, there is an insulator in between, and you cut a hole and you insert, and that metal is available in that hole also, which ensures an electrical connection between these two metals, right? So instead of having just one wire, generally the size of the wire is fixed. Okay, so if you want to make a better connection, you can there won't be any option of increasing the size of the wire. You can't make a big hole and punch through and fill metal here. What we can do is, because the sizes of the wire will be fixed by the fab lab, okay, because of other design constraints, so we can use a large number of wires. Okay, so this is what, now if you see here, it's a corner out here, so you see lot of wires have been used here, so that there is no crowding around of electrons in the corners. So you got to be careful with these kind of designs. Okay. Now we talked about wire resistance till now. Now we will try and understand a little bit about the wire capacitance. Okay. Now if you see here, this is an conductor wire which is shown here. Okay, it is running into the paper. Okay, and these are running along with the direction of our screen. This is going into the screen. So I said that adjacent layers will be running orthogonal. Okay, so this is in XY direction, and this is in the x-axis. Okay, both these, they are running in the x-axis. This is running in the z-axis. Okay, into the screen. Okay, and coming out of the screen out here. So only the cross section is visible from here. This is I have 3 metal layers. So one is I have a C top, which is the capacitance associated with this wire with the top layer, and then I have C bottom, which is the capacitance associated with the bottom layer, and within this layer there could be some adjacent wires also. So these are the C adjacent. Okay, so there are 3 capacitance out here involved out here, right? Okay, now if you see here, this is the H1 and H2 is the gap, silicon dioxide gap between this metal layer and the next metal layer. Okay, and T is the thickness of this particular metal which we are interested in now. So the total capacitance will be some total of C top, C bottom, and 2 C adjacent. Because both sides there could be wires. So this is the total capacitance as seen by the wire. Okay, so you can actually think of it as a parallel plate and a capacitor, where C will be given by epsilon A by D. Okay, now in many technologies, Okay, epsilon is silicon dioxide, right? So to increase and higher capacitance always is going to degrade your overall performance. Now in certain technologies you have some vacuums also, right, in between, okay, which increases the value of epsilon. Okay, so if you see here, vacuum gaps are there between various metals. Okay, metal layers. So it is not fully silicon dioxide. So small vacuums also will be there. Okay, so that will increase the decrease the value of the capacitance. Okay, so you have an epsilon for silicon should be close to, I think, 3.9. Okay, so for vacuum it will be much lesser. So so you can so this will be the overall capacitance can be decreased by using vacuum also out here, right? Now like for metal, we had an figure of merit. If I go back here, this, right, sheet resistance, okay, was defined here, and then we multiplied it by L by W to get the resistance, right? In the case of capacitance, I have also generally the now here the capacitance is defined is defined as some microfarad per micrometer, okay, of the length of the wires. Okay, now generally it is 0.2. Now we might thinking, why is that width of the wire is not scattered here, right? Only the length of the wire is scattered here. Okay, so you just keep a note of this. I will just explain this aspect in the next slide. But always remember, for a resistance, whatever is the sheet resistance, we are multiplying it by length and dividing it by W. Whereas for an capacitance, okay, we have to just multiply it by the length, and we are not taking into consideration the width of the wire. Okay, typically it is 2 femtofarad per micrometer. Okay, so now let's see why that is happening. So if you see here, this is the metal which is running here, right, and this is the gap, and this is the bottom metal out here, right? This is the thickness. Okay, now if all the electric field is confined in between these two regions, if it is going vertically from top to bottom, okay, then it can be termed as a parallel plate capacitor. Okay, but in deep submicron technologies, okay, what happens is these widths are all in nanometer range. Okay, so a lot of the electric field doesn't get confined in that narrow region. Instead, they will come from out and get coupled here like this from outside. Okay, so that restriction of width no more remains out here, right? So the electric field is not constrained to remain within this width. Okay, because it is in nanometer scale, deep submicron technology, the electric fields can come from this surface, and through the insulator it can get coupled out here, right? So that is the reason. So that is known as a fringing model. So if somebody is interested, you can this is an you can go through what is fringing model, and you will find some literature available. You can get into it. Here, if you see here, the capacitance is proportional to log of W, not directly W. Okay, so you can consider that it is kind of independent of W, and that is why when we talk about 2 layers of wires, we generally speak in terms of L and not in terms of W, and that is why we are calling it around, okay, the capacitance have this much femtofarad per micrometer, right? So so this is for a metal layer. Obviously now if you see for the gate, okay, the gate, the capacitance will be higher. Okay, now why is it that the gate capacitance is higher for the polysilicon? Because for the device to work properly, we require a greater coupling, right? So the gate is designed that way, that the T oxide between the poly and the substrate is as thin as possible, right? So you can't increase the T ox there. So that is kept very minimum. because you need to have electrostatic coupling between the poly and the substrate for the MOS device to work well, right? So there it is desirable to have, you can't have, if there is no capacitive couplants, then the channel formation will get affected, right? So if you see the ID equation, there is one Cox which comes, right, and ID is equal to mu1 Cox W by L. So Cox for greater ID, Cox has to be greater, right? So gate, as far as the gate is concerned, you will have a higher, the thickness of the oxide is kept as minimum as possible. You can't keep reducing the thickness, because after I guess 2 nanometer, okay, physically then there will be punctures and junction failures. So it is generally the minimum thickness which is possible is around 2 nanometer. Okay, so for the gate it is kept as close, for the gate oxide it is kept as minimum as possible. So it is around 2 femtofarad. Whereas from metal 1, when I move from metal 1 to metal 2, okay, I can have large gaps out here also, okay, because now that capacitance is not desirable one. Okay, so that is why so you can so this has the difference here, right? So that is will be specified, okay, what metal will have what kind of capacitance. Generally it will be a fraction of a femtofarad, right? Whereas the gate capacitance is approximately 2 femtofarad per micrometer. In both the cases, and we don't take into consideration the W, okay, only the length. Okay, so this has to be kept in mind out here. Okay, whereas for adjacent layers which are running like this, okay, generally here it works like a parallel plate capacitor. Okay, when if you are running like this, okay, in that case we can use this parallel plate capacitance formula. But this is very again it is avoided in design. Also, so this T is pretty small, right? It is again in few nanometers only. So more the thing, the more dominant capacitance is generally the one between the layers. Okay, so this is not very dominant because T is very thin for most of the metals. Okay, so and also we don't run two lines parallel to each other for a long distance. So that is about the capacitance. So one more caution about the polysilicon. So FUs it has lower it has got a higher resistance. It is only used for transistor gates, so just use it for short wires between gates, and don't use it as an wire. Okay, similarly diffusion also you will have diffusion also. That is again within the within the substrate you can have diffusion layers which is highly doped regions. Okay, please don't use that as a, because some of that is used to fabricate resistance and all, but never used as to make interconnects. Okay, so for all interconnects please use metal layers which is provided by the fab lab. Okay, and now if you see the model, okay, so there are you can model that as an resistance and an capacitance. Okay, so if you see here now the L, this is known as the L model. Okay, where you represent it by an resistance and a capacitance. This is known as a pi, where you compute the capacitance and you split it into 2 and use it like this. And this is known as an T model. Okay, where the resistance is divided into 2 and you use a single. So in this pi model, again this once you compute the total resistance and total capacitance, then if you divided it into three segments again, okay, then it will be, the accuracy is close to between the simulation and the measured result is close to 3%. Yeah, sorry for the disturbance. Okay, so this is what if you use a pi model and you further divide this into 3 segments, then your simulation results will be close to the actual measured results. Okay, but what we are going to do for our exam and numericals is we are going to use the pi model, single segment. Okay, we are not going to divide it into 3 modules. Okay, so this is an L model. You have RC, RC, RC. You can represent it like this. Again, please don't use it for your exam. I have put this model just to bring because just to explain that the length of the wire has an quadratic function. Okay, the delay is a quadratic function. So this is true even for all the models. Okay, so just for simplification, I have used this model out here. Okay, so you have R1, C1, R2, C2. These are the n segments. Okay, so instead of having a single R and C, n segments has been shown out here. So C1, R1. Now this delay here it's an RC delay, right? So this delay out here will be C1, R1. This delay out here will be, now this node needs to be charged. Okay, so this will be R1, R2 plus C2. This will be R1, R2, R3 plus C3. So you write this equation. Is this clear how this equation has been written to all of you? Because there will be some problems like this. So that's why I want you to be clear on how this equation is written. Okay, is it okay with all of you? Yeah. Okay. Can somebody respond? I'm audible, right? Yeah. Okay. So this is the equation. Now each of them, if I replace like C, I replace it with L is the total length. Okay, N is the number of segments out here. So L divided by N. Okay, C I am going to replace the N, and C is the capacitance per unit length. Okay, so I have replaced it C divided by C here. Now, so this has been replaced by L by N here. So similarly, R has been replaced by L by N into small r. Okay. So if you do that, so you will get you can bring out this L and C for R and C out here, right? If you do that, if you see here, okay, this is not an important equation. Only thing which we need to remember here, and okay, the takeaway out here is if you see here, and it becomes L square. Okay. That means the delay of the wire is a quadratic function of its length. Okay, because if you keep increasing the length, not only the resistance increases, but the capacitance also increases. Okay, so it has got a very dominant role to play in the total delay which comes in the wire. So you have to be very careful. So you can't arbitrarily keep increasing the length of the wires. Okay, so you have to be careful, and you have to try and minimize the length of the wires. Okay, so that is known as the lumped element model. But you will have some numericals like this. Okay, so let's try and understand how these numericals are to be solved. Okay, so it says metal to wire in 180 nanometer is 5 mm long. Okay, and this much width. Okay, now what would be the total resistance? Now total resistance, I need to compute the number of squares. Like I said, when I compute the number of squares, L divided by W. Okay, it is not L into W. Okay, so this is the mistake generally many of the students make in exam, because this square term is slightly misleading. So you try to multiply these two. Okay, so it is a division out here. Understand here in this particular square is not L into W, L divided by W. So you get a 15625 as the number of squares. Now how to compute the resistance? Okay, it is the number of the value number of squares into the this is given, the sheet resistance is given as 0.05. So you multiply with the sheet resistance, you get the total resistance out here, right? Now similarly, the capacitance of the wire is given as 0.2 femtofarad per micrometer, right? In this case, I am not multiplying it with the W. I am just multiplying it with with the length. Okay, so I get 1 picofarad, and then since I am going to use an pi model, I am going to split it into 2. Okay, so 781 resistance here, 1 capacitance here, 1 capacitance here. Okay, this is how this wire has been modeled out here. Okay, is it okay till here? Okay, this has to be clear. If it's multiplication, it comes as 1600. What comes as 1600? This one. Uh, 5000 into, yeah, it is division, right? Right. So we need to divide it, right? Yeah. Is there a doubt? I couldn't get what is the issue? This is the length. This is the W. Okay. It's a division out here. Okay. Okay. L by W. Yeah. That's what I said. Again, we should not be confusing it. Number of squares means L divided by W. Don't go by the term square. Okay. It is L divided by W. Okay. Keep that in mind. Okay. That's what I wanted to say. Okay. Now if you see the problem, something would be like this. Estimate the delay of an 10x inverter driving a 2x inverter at the end of a 5 millimeter wire from the previous example. This is the 5 meter. We have already computed this model out here. Now we are going to use that model out here, right? Now it says a 10x inverter is driving. Now the inverter, okay, 10x inverter will be modeled as an resistance, okay, and the next stage, the 2x, okay, that is the load. So that will be modeled as an capacitor. Okay, so this is a resistor, and this is a resistor, and this is a capacitor out here. Obviously, we are neglecting the drain capacitance of the driving. So there will be a drain capacitance out here, right? That comes from the inverter. So we are assuming that drain capacitance is negligible. Okay, only the gate capacitance of the stage which is being driven, that we are catering out here. Okay, so if it is not specified, the drain capacitance, you can assume that is negligible. Okay, here now if you see here, unit inverter, it says it is 0.36 micrometer NMOS and 0.72 PMOS is the unit inverter, so that the resistance are equal. Okay, so you have twice PMOS size is twice for a unit inverter. Okay, now okay, let's see what it is written here. Unit inverter effective resistance is 2.5 kilo ohm per micrometer. Okay, now if it says that unit inverter has got 2.5 kilo ohm, right? Now here if you see here, we are not going, it is defined like this, into micrometer. Okay, so that means it is only catering for, so if you are using an length is constant here. Okay, so we are not going to, that is for wire where we are catering for length. For an unit inverter, when they say, it is assumed that all the inverters and all the CMOS devices are going to have uniform length. So we just have to multiply it with the width factor. Now since this, it has got 6.k kilo ohm, a unit inverter has this resistance, I am using an 10x inverter. That means the width is large. So obviously I have to divide 6.9 by 10 to get the effective resistance. Is this clear? Let me explain you once more out here, right? When I say unit inverter, right, has got a resistance of 6.9 kilo ohm, right? Now I am using an inverter of size 10x. Okay, 10x obviously doesn't mean that the length is increased to 10x. Okay, it is always that the length of all the MOS devices in a digital circuits is kept to the bare minimum. Okay, minimum possible defined by the technology. It's only the width which we keeps increasing. So when I say 10x, it means the width is increased. So if I say 10x, the width is increased, so the resistance has to naturally come down by a factor of 10. So 6.9K becomes 690 ohm. Obviously, the drain capacitance by that driving transistor also goes up, but in this particular example, it is told to neglect that capacitance. So we are not taking into consideration that capacitance. Is this clear? How did we get the 690? Yeah, is it okay with all of you? Okay. Now the next thing is from the load side, you have it says the unit inverter has got 2 femtofarad gate capacitance. Okay. Now we are using an 2x inverter, so the gate capacitance will be 4 femto out here, right? Okay. This is one. Okay. See, this is how they have said this is the value which they have got for this is per micrometer. 2.5 kilo ohm is per micrometer of the width. Okay, it has been defined out here. So they have divided it by the width out here, right? So that is why we are doing it. Generally, empirically, this is the formula which is used for most of the technology. This is 2.5 kilo ohm for NMOS divided by W by L. Okay, you get the value of Rn and Rp. Okay, so this is what empirically it is done. This is for NMOS. This is for PMOS out here. Right. This is for NMOS. Right. NMOS. Obviously, for PMOS, this 2.5 will be 5, and hence 0.72 has been used. Okay. So we don't have to get into these details. If this figure is given, we can straight away assume that this is for a unit inverter. So okay. So if this is given, if the question asks you to compute this, you can use this formula. Otherwise, if this value is given, then you can straight away use this value. Okay. See, if this is for unit inverter, and for 2x, it will be 2. For 10x, it will be 10 divided by 10. For 2x, it will be divided by 2. Whereas the capacitor, it will be for 10x, it will be into 10, and for 2x, it will be into 2. Okay, so you can do it that way. Okay, now here the load capacitance is 4. Okay, now I want you to compute this yourself and verify the results. Now this is known as how to compute this. We use a formula which we learned here. Okay, Elmore delay model. Okay, what is Elmore delay model? That is the method of computing the delay. What we do is, you can, if you have a paper and pen, you can note it down also. 690, okay, into 500 femto. Okay, so that is plus. Now, what is the next stage? 690 plus 781. Okay, into 500 plus this 4 femto. That is 504 femto. Right? So that is it okay? It is like this. This is again Elmore model. R1 plus C1. Okay. Then you have R1 plus R2 into C2. No, R1 C1. Okay. R1 C1 plus R1 plus R2 C2. Okay. So these two terms will be there in that particular case which we are referring. R1 C1 and then R1 plus R2 and C2. Okay. So that is the thing which is there, right? So you have an R1 out here, right? And what is the capacitance? Just 500 femto. Then R1 plus, that is R1 C1 again. Then plus 690 plus 781. And what is C2? These are in parallel, so it becomes 504. So you compute that and you try to figure out if it is coming to 1.1 nanosecond. Okay. So this is how the delay is being computed. Okay. And also we can have, instead of having a long wire, if there is a requirement, we can have an in between repeaters. Okay. So you can divide it into, and you can place inverters in between. Okay. So that will speed up. Okay. That will reduce the now if you see here, now these inverters have been placed out here. Okay, what we are doing it, this is the equivalent circuit for one particular stage. Okay, this is R divided by W. Okay, that is if R is the resistance for a unit inverter, and W, if you are using a larger width, so it becomes R divided by W. Okay, this is the now here we are putting it the capacitance which is coming from the inverter side also. So this is C into W. Okay, C into W, right? And what is this P inverter? W is the width of the transistor, right? And CW is actually the gate capacitance. Okay, so how much is going to be the capacitance at the output, right? That will be only a fraction of that, right? Because gate capacitance is CW, right? But whereas P inverter is just means at the output only a fraction. So P inverter is generally 0.2. In the earlier case is approximately equal to 0.5. So this we had neglected in the previous example. Here that is been also included here, and then you have this pi model coming here. Okay, so RW L by N, CW L by N, and then this is the gate capacitance of the next stage, CW. Okay, since it is the gate capacitance, you don't have this P inverter thing out here, right? Now if you see, if you write the Elmore delay model, so for this resistance, I see one CWP inverter, right? And for this resistance again, I see these two capacitance also. So they also have been returned. So this is CW, so CW plus this is CW P inverter out here, and these two capacitances also, right? So it is CW L by N, and for this resistance only these two capacitances come out here. So these two capacitances have been returned here. And now what they have done is here in the textbook, they have kept assumed N to be a variable and W also has to be as a variable, and they have differentiated it and equated it to 0 to find out what would be the optimum number of stages for a given particular for a given length of wires. Okay, so they have differentiated it and they came up with this formula out here, right? So L divided by N. So this is the formula which can be used to compute the total number of inverters which needs to be inserted out here. So so a value of N is given out here. N can be computed by using this formula, right? And also so we have assumed that the value of RC is given for an inverter, right? And also for a fan out of 4 it will be 5 RC. And again one assumption which is made out here is if the gate capacitance is 1, okay, the drain capacitance at the output will be 0.5 times. Okay, the entire gate capacitance will not be reflected as a load capacitance by that intrinsic load capacitance by that inverter. So they have taken it as 0.5 out here, right? And instead of, they say if an inverter fan out of 4 is defined, then this equation can be represented like this. Okay, with that again some substitutions they have done, and a delay and the width has been computed here. So you can go through these derivations. From the exam point of view, it's not this particular calculation is not important, whereas this thing is important. Okay, so I'm not going to set a question based on the repeaters, but the concept of repeater should be clear to all of you. Someone who is doing working in this domain needs to understand that we can reduce the delay by inserting inverters in between, and there is a formula which exists, okay, to compute the number of would be the optimum number of segments. Okay, it is not that arbitrarily you put some inverters in between. So what should be the value of N to get an optimum delay? So there is a formula which exists, so you should know that. Okay, so in case you are going for a design, and what should be the size of these inverters, and that also a formula is given based on the values of the wire resistance and wire capacitance and the total length. So such kind of mathematical analysis is also available, so that you need to keep in mind. Okay, can how TPD, right? This TPD, right? It is like, what did we do here? R into C, right? The same thing has been done here. It's only see this R into this C, okay, plus this R these two CES are in parallel. So this R into this C plus this C, again this R into this R plus this C plus this C, right? So now this R is seeing this capacitance, this R is also seeing this capacitance and this capacitance. So it is written in that manner, so it's looking a bit confusing. Otherwise it is the same approach. So this resistance is going to see this capacitance and this capacitance in parallel, so they get added up, and in the next stage we say this plus this into this, right? So so that is why we have here it is, this particular resistance is taken out in common, and all the capacitance as seen by this resistance is written out here. Okay, but by adding inverters, shouldn't the delay increase? No. What happens is what happens, these inverters, they have a threshold. The moment this input reaches close to half, okay, this will trigger these inverters. Okay, that is why it reduces the delay. Okay, is it okay, Indranil? What happens is, suppose you have a single wire. Okay, it is taking a total 10 nanosecond for this to rise to half the VDD. Now suppose I have put two inverters in between. The first inverter, and it is in between, so within 2 seconds it will reach the switching threshold of that inverter, so that will trigger an output swing. Okay, so again that wire length is again short, so that will again trigger, because the inverter threshold, the moment it reaches the inverter threshold, that will trigger a change in the output. So obviously power will be more, but then it will decrease the propagation delay. Okay, that is how the repeaters will. Okay, so just another 2 slides, and then we'll take a break. Okay, so what is crosstalk is when there are 2 wires which are running adjacent to each other, or on top of one top and below. Whenever there is a change in data in one of the wires, okay, some capacitive couplings would happen, and it can change the state in the other wire also, right? So that is known as a crosstalk. Okay, so whenever the data is changing in one wire, okay, because of the capacitive couplings between the wires, so in the next wire, in the adjacent wire, or in the top or bottom wire also, the data can get changed. Okay, so that is known as a coupling or an crosstalk. Okay, so so if you see here, okay, here now this is A wire and B wire, they are running close to each other. Okay, so now suppose B is constant. Okay, in that case, a change in VDD, okay, we will so if you see here, the net capacitance seen by this wire will be C ground plus C adjacent. Okay, this is the substrate. So so this is the kind of capacitance it will see. This is the you can call it the next layer also. Suppose we are not now we are talking about only the adjacent wires, we are not talking about the wire which is below. Here they are running in parallel to each other, so you will find C ground plus C adjacent, that is the capacitance as seen by this wire. Now if both the wires are making either 0 to 1 transition and 1 to 0 transition in sync, if they are doing in sync, okay, then delta V will be 0, so then this capacitance doesn't play any role. Okay, however, if I have this making a transition between 0 to 1 and this is making from 1 to 0, then the net capacitance as seen by this wire will be 2 times the C adjacent. Okay, so it is like it get multiplied by 2, because this is making an opposite transition. Okay, so so this is how crosstalk affects, right? So if this is making a 0 to 1, this is making 1 to 0, so you can assume that this wire is going to see a large capacitance out here, so it has to overcome that capacitance also. Okay, so we'll just take another 2 slides to further analyze what is happening. So if you see here, this is the aggressor line. Okay, that means the line in which the data is changing. If the adjacent line is just hanging, okay, so that's it's just called an victim line. It is just hanging in air. As of now, it is not being driven by any output. It is just hanging. So this is the adjacent capacitance, and this is the ground capacitance of that victim. So when this makes a transition by delta V, okay. So the net voltage change which will be experienced by the adjacent line will be given by this formula. This is just a potentiometer rule, right? This we probably saw in dynamic circuit, this derivation, where the right in your last semester you might have done the charge sharing issue. Similarly, same thing happens out here also, right? If this is not being driven, okay, and then you have a transition being made by the aggressor, then a portion of the voltage gets coupled to the victim, right? And that voltage which will be available on the victim will be given by this formula, C adjacent. Okay, is this okay? This formula, right? This is making a transition from 0 to VDD. Then what will be the voltage out here? Okay, if I have to compute, if this was initially 0, it is hanging in air. Okay, it is not being driven by anything. Okay, it is just a wire. Okay, and that wire has gotten stray capacitance with respect to ground, and it has also gotten C adjacent, which is coupling these two lines. Then the net voltage after this makes a transition by delta V aggressor will be delta V victim given by this formula, C adjacent divided by C ground plus C adjacent. Okay, is it okay with all of you? Okay, so this is the net voltage which will be seen on this line after this makes an transition. Okay, because of these two capacitance. Okay, but in case this line is being driven by an inverter, right? If this is being powered either to VDD or to ground. In this example, we are assuming that this line is being connected to the ground. Okay, but there will be some resistance of the NMOS, right? So the right, if it is being driven by an inverter and this is being pulled to ground, so you have an NMOS, right? This resistance is known as the resistor victim. Okay, that is, it is nothing but an resistance of the NMOS inverter, which is trying to keep this as 0. So whenever there is a switching happening out here, you will find that the line here, which is supposed to be 0, okay, it will make a bump and it will come back to 0. It will make a bump and it will come, because some charge from here to here, although this line is, I am transmitting a 0 in this line. Okay, how am I transmitting a 0 here? There is an inverter out here, and through the NMOS of that inverter, this line is connected to 0, right? But this line is making a transition from 0 to 1 because of the capacitance which is there, which is coupling these two lines. There will be a bump out here. Okay, the output voltage will increase and it will come to 0 out here, right? Now it says here, if this transistor is very weak, then the bump will be increased and it will remain for a large time. Whereas if you see here, victim size is being increased, then the bump will decrease. So whenever you are making an driver transistor, so if there is a possibility of higher capacitive couplants between adjacent lines, then your drivers should be strong enough so that this bump is minimized and it comes to 0 as soon as possible in the time. This is a time. So within few picoseconds, this has to settle down. So because when the data is changing here, some stray voltage will be picked up by this line, and if you want to continue it to remain 0 or 1, then that particular transistor, which is that driver which is driving this line, has to be strong. So so you have to cater for those kind of crosstalk issues also when you are designing your drivers. Okay, so I think we'll take a break out here.